going to challenge problem 1, paper boomerang.
Jack, blue chip. Please choose another one.
I'm going to challenge problem 2, air muscle.
What's that?
Write down the name of the representative of each team. Before that, there is 5 minutes to prepare. Okay, the recorder ends, so you have 10 minutes.
Hi, I'm the reporter from Haha, and I'm Zoe Chi. Today I'm going to present number 2, air muscle. And this is the problem statement. Place a balloon inside a cylindrical net and inflate it. The net will expand and shorten. Investigate the properties of such a muscle. The main focus will on the expansion and the shorten of the net screen and the loading and the force of the air muscle. This is our outline. And this is the observation video. Through this video, you can see that the beat is changing like this and this. So I'm going to investigate this. And then I'll suppose this is lateral and this is axial. First, let's talk about the theory, Young's module. Young's module is the fundamental material properties that describe the stiffness of the material. And it quantifies the material's ability to resist deformation under axial, tensile, or compressive stress. And this is the equation, E equals to stress divided by strain. And usually the unit is GPa. The higher values indicate different materials such as steel. And when the stress-strain diagram is linear, then it means that the material is a linear elasticity. The second one is I'm going to define the eta. Eta is the measure of how much axial strain occurs while minimizing lateral strain. And this is the equation of eta. The strain of the axial is calculated as the change of the length divided by the original length. And when, for example, when eta is 100%, then it means that all deformation is axial, meaning the structure is ideal for actuation. And when eta equals to 0, means that the system is inefficient. And this is a visual representation of the deformation pattern. The blue is the lateral and the white line is axial. The third, and then this is a theory of the ideal gas law. PV equals to nRT. For a balloon in the net, inflation increases pressure pushing against the net. The nets restrict axial extension, causing lateral shortening, just like the muscles. And this restriction amplifies pressure changes, leading to a nonlinear pressure-volume relationship where resistance increases with expansion. And this is my theory deriving. And I want to know the pressure of the balloon. So this is the equation. And because the gas I inflate in is the air, so then I can bring this into the equation. By controlling the temperature and R is the constant, so I can eliminate R and the T. Eventually, I will get this. So by seeing these equations, you can know that the balloon's internal pressure depends on the total volume of gas and the current volume of the balloon. And since the pressure of the net was given by the balloon, so you can equalize them. And we relate this pressure to the mechanical response of the material. And this is my experimental setup. I have two ways to inflate the gas into the air muscle. One is using the syringe. By using syringe, I can control how many volume of gas that I actually put in. And using the three-way divergent values to control where the air goes. And by using heat shrinking tube, drawstring to fix the size of air muzzle. And the mesh I use is snakeskin net. How do I record the changes of the grid? I use the camera to record the inflation, and then use image J to calculate the strain. My second way to inflate gas in is using the electric air compressor. Here what shows what's the pressure currently in the balloon right now. Then I can double check if the Young's module I calculate is correct or not. there's two values in my experiment, and one is the width of the net, and the other value is how many layers of balloons did I use. This is the result of eta. From this chart, this chart compares eta from one layer and two layers balloons structure across different mesh diameters. And through this chart, you can see that eta increases as the mesh diameter increases. And the maximum efficiency is at 2.9 cm for the one layer balloon. So by this equation, you can know that when this is decreasing, this eta will increase. And this is my result for the Young's module, the ACO part of the Young's module. And you can see that the modules decrease as the mesh diameter increases. And if you want to ask why is there differences between these different diameters of mesh have different Young's modules. Although it's because that the ring angle with different diameters changes at different speeds during expansion. So that's why there are slightly differences between them. But however, all the mesh, the materials of all the mesh is the same. So that's why the differences between them are small. And by looking at the chart below it, you can see that the strength and the strain relationship is linear. So I would say that the material behaves elasticity in this range. And this is the lateral Young's module. You can also see that it's linear relationship between them. So it's also elasticity. And by comparing these two together, you can see that no matter which, both the axial and the lateral direction are elasticity. And since the slope of the stress-strain diagram refers to the Young's module, so by comparing these two slopes, you can see that the literal Young's module is bigger than the axial. And what does that mean? It means that the literal is stiffer than the axial. So, and then by comparing the two ways I used to inflate the gas in, from this chart you can see that they're almost the same. And this is my second experimental setup. This is the air muscle, and by using this Pascal Smart card to know the force. And there's two values in this experiment. One is the length of the air muscle, and the second one is the width of the mesh. And this is the result of the force output. From this chart, we analyzed the force output air muscle with different length and mesh diameters. From the bar chart, we can see that each length, a small mesh diameter produces higher force, when a larger, and the wider air muscle reduces axial force output. So that's why wider air muscle produces lower force. And then the shortest and the narrowest air muscle perform the greatest force. And this is my result for the force load on air muscle. You can see that longer mesh shows higher contraction ratio compared to shorter one. And as load increases, construction ratio decreases for all mass lengths. This is expected because air muscle has a limited construction ability, and as the external load increases, it struggles to contract as much, and the construction differences between the 50 cm and the 20 cm is small, meaning after a certain length, increasing mesh size has decreasing effects on construction performance. And by seeing the 10 cm mesh, you can see that it shows the steepest decline, and meaning it loses construction efficiency faster with increasing load. And this is the construction equation, construction ratio equation. And by comparing these two, you can see that the force is influenced by its initial length. Longer muscles experience greater axial construction due to their increases length, but the force is distributed over a longer deformable section, leading to a reduction in overall force output. And by conclusion, there's three key factors that affect the efficiency of the air muscle. One is the axial to lateral ratio, and the second one is the force output, and the third one is the construction ratio. And this is the comparison of the size of muscle have the different result, and this is the compared to the actual muscle and the air muscle.
Okay, time is up. Okay. The opponent, please questions in 2 minutes.
Did you stretch the neck or the balloon before you pump the muscle?
No.
Did you only visually confirm the cylindrical shape of the neck throughout the experiment?
Sorry again.
Did you visually confirm the cylindrical shape of the neck throughout the experiment? Yes or no?
I use image shape, so I don't use
Okay, thank you. Did you assume the balloon will maintain the same shape throughout your experiment? Will it maintain the same shape? The balloon.
Yes.
Okay. Did you consider the air pressure and temperature inside the balloon to be uniform while pumping?
Yes.
Did you measure the maximum shortening percentage of the neck?
Maximum short.
Like the maximum contraction of the neck?
I did.
Okay. Did you measure the volume of air needed to achieve and certain shortening?
Yes.
Was inflation pressure controlled and measured? Was pressure measured?
Oh, yes, I did.
Okay. Did you ensure there were no leaks in your balloon inflation system?
No leaks.
Like air leak out of the...
No, because I use
Okay, thank you. Did you consider the energy efficiency of this muscle?
I consider the efficiency.
How often do you change your balloons for your experiment?
Once. I use the same balloon,
So
but
you didn't change it?
I change it every time. But I use the same balloon when
Same kind of balloon?
same kind of balloon.
Okay, thank you. Did you analyze the maximum force the muscle can generate?
Yes.
Okay, time is up. The preparation of the opponent in 3 minutes. component is the most performance represented?
Honorable judges and fellow competitors, I am an opponent from Team Excelsior. Today I will be opponenting air muscle. Place a balloon inside a cylindrical net as is sometimes used to wrap garlic and inflate it. The net will expand and shorten. Investigate this property of such a muscle. Today we will focus on how is the contraction of different muscle different and what different parameters can be investigated in this experiment. This is the outline of reporter. The reporter used Young modulus and ideal gas law to explain the phenomenon, and the experiment she did was the length of the air muscle and the different layers of balloon, and the net width and the volume of air pumped into the balloon. However, there are some controversy and deviation in the experiment, like friction and the initial shape of the net has to be measured, and the ball position inside the muscle has to be in the center, and the temperature has to be consistent, and we have to also investigate the shape of the balloon, will it change or not. This is the strong and weak point of the reporter. She had a demonstrated phenomenon, however, she lacked explanation of deviation. She had explained the cause of phenomenon, however, she doesn't have a theory line to compare it with the experimental data. And she also had a clear observation video and the explanation of theory. However, she lacked of error bar and no boundaries in some cases, and she doesn't have a force analysis to draw the force, and the reproducibility of this experiment is low. Today we are going to discuss viewpoint. First, we will discuss about the force analysis, and we will include friction, and we will also include ideal gas law, and also the contact area in the balloon and the net, and also the shape of the net and the balloon. About the data analysis, we are going to analyze the contraction and the force of the muscle. Here are some possible errors, like the initial shape and the length of the net, and the balloon position inside the muscle, and temperature, pressure, consistency, and the shape of the balloon. And next is the parameters. The reporter did not discuss about some parameters like the net elasticity and the thickness of the net, and also elasticity fatigue of balloon and net. Because like elasticity fatigue may happen after you pump many times of the balloon. And next is the gap of the net. And finally is the different material of the balloon. The opponent wants to skip the section. Judge, can I use the blackboard?
Yes, sure.
This is the balloon, and this is the net. Can you draw the force diagram? Yes.
And actually, the balloon is like this.
Oh, I thought. Okay. So what is this force?
The force that was
Surface tension or?
inert pressure equals to the outside pressure that it gives to the net. So that's why I used the ideal gas law.
Okay, thank you. And so this is the only force used in the experiment.
This is the only force that I considered.
Okay, thank you. And can you please turn to the page 16 of your PowerPoint? Did you mention how you inflate the balloon?
In this experiment, I'll inflate the same volume of the balloon.
How did you inflate it? With?
Syringe.
Okay, thank you. Can you turn to page 19? Can you please explain why these two lines are very close and it is hard to choose this line?
Okay, because here I did mention that there's a certain limiter, and that's expected. So that's why they are very
Oh.
similar.
Oh, thank you. Can you turn to the theory, like the Young's modulus? Can you please explain why Young's modulus can be applied to this problem?
It's because the Young's module is to quantify the material's stiffness. So so that's why I'll use it. And also that if the stress strain diagram is a linear relationship between them, so that I will know the material is elasticity.
Oh, thank you. Okay. Did you ensure the cylindrical shape of the net was maintained and consistent every time you reset your experimental setup?
Let me tell you like this. When every time before I do the experiment, I'll make sure that I'll input the same volume of the gas, and then to make sure that I'll put the same volume, and then I'll see that the inflation. So that's the same, so that I will know that it's not out of the elasticity range.
Okay, thank you. Next, this is the chart of, this is volume and this is the force of the muscle. Can you draw the relationships between these two?
In what condition?
Like, what condition, like, hot when you inflate the balloon? Any certain conditions?
In my experience, if I consider the small, you mean the force?
Yes.
Okay. In my experiment, I used the smallest, and
Yes.
and then the volume, you mean
Like the volume of the balloon.
the volume of the balloon, how many do you know that I can say it?
Like, just calculate the volume of balloon when it was inflated, like this volume. Can you
Okay.
please draw a graph, please? Um, oh, okay. The opponent actually thinks it shouldn't be like this because the volume has.
Sorry,
Okay.
can I do this?
Yes, please. Yes, please.
Because there's tension of the, there's force, sorry. The mass will limit how many, how much volume the balloon increase, right? So there will be a,
Faster, please.
there will be a certain, it will be limited, so it will not increase forever.
Also,
There's a-
boundary.
Yes,
And what is the boundary? Did you measure it?
yes, but different condition of the mass has different boundaries.
Okay. Actually, honestly, the opponent really suggests that the volume has to be like to a certain magnitude, so the volume is big enough to stretch out the force. Because when the volume is zero, the force should be zero. So like so the force should be like this, not start from here. Because the volume of the balloon has to be big enough to expand the mesh. Okay, thank you. Since you mentioned about PV equals to nRT, right? Why do you think PV equals to nRT is able to be used in this experiment?
Because I think this is enough for me to
honestly, the opponent really suggests the reporter to use another type of formula, and this is the van der Waals theory.
Yes, but I consider it, but I think that's not necessary.
But however, because van der Waals theory considers a low pressure, and the pressure inside the balloon is
It's very big.
No, it's low.
It's big because if I use this, I'll inflate it until it's straight. And then the pressure will be very big. Because, do you know why?
Okay, thank you. Let's move on to the next section.
And further, how do you define the big pressure and the low pressure?
Let me explain. When the mass inside the balloon, when the pressure is very big, the force between the mass inside will be very big.
I know what you mean. But remember I just mentioned, I said it will be a boundary if you inflate gas in, and then it will just explode if you keep inflated gas into it. So that's why I consider the pressure of the balloon is big.
Okay, I understand your idea. Do you think the temperature inside the balloon maintains the same?
Yes, I believe. Because
Did you measure it?
let me tell you, this is the previous value of the survey. And the gas I inflated in is the outside gas.
Oh.
So that's why.
So you didn't really measure it, but you considered the temperature the same.
Yes, and
Okay.
furthermore, if you think, why do you think that the temperature is not the same?
I didn't mean the temperature is not the same. I'm just asking.
Okay.
Did you control the pumping speed while you are pumping the balloon?
Yes.
And is it uniform every time?
Yes.
Okay, thank you. Did you measure the surface tension of the balloon?
I believe that if it's to the certain boundaries, then the surface tension is very high.
Okay, so the opponent really wants to suggest a way to calculate the surface tension because this is a balloon and the surface tension will be equal to P times the radius of the balloon divided by 2. So, corresponding to the question I just asked the reporter to draw, the opponent really thinks the real force diagram of this balloon is like this. The balloon will have a force that is delta P times A. And A is the surface area that the balloon has contact with the mesh.
Sorry. Why does your balloon look like this? The balloon looks like this, right?
Oh, sorry. My bad. So this is the force of the balloon. And there will be a surface tension like the force of the balloon in here. And here. And there will also be the tension of the net.
Okay, time is up.
Thank
The
you.
opponent, please summarize the discussion.
This is the discussion summary, and the opponent thinks the reporter lack of force analysis and the elasticity range has to be considered. And the ideal gas law cannot be applied to this experiment because the pressure is low. And the reporter should measure the pressure and temperature with something like Arduino sensors to ensure really the pressure and temperature is the same. And multiple layers of balloon may cause deviations. And there should be surface tension calculated in the force analysis. And the reporter's way of inflating the balloon
Okay.
has to be considered.
Questions from the reviewer.
Okay, now here is the question from reviewer. First, I want to ask about the elasticity of the balloon. Did you consider that?
Yes, because that's linear.
Okay. And however, do you think the elasticity of the balloon is critical?
Yes, it's very good.
Okay, so you mentioned the Young's modulus, and the Young's modulus is used to describe a material. And so, do you think it is like suitable for this condition since it has two parts, the net and the balloon, and it's not a single material?
Because the Young's modulus that I calculate is the net.
Or the Young's modulus of the net?
Yes.
Okay, and next question. I mean, the grid will expand, right? But different parts of the grid, do you think they expand?
No, they don't expand the same, but I'll track the same grid, and then only in the middle. Because here, obviously, that's not the same. But in the middle, because it's cylindrical, so that's why I suppose that the middle grid will be the same.
Okay,
Can you
and
rephrase the question?
I'm asking another
Oh,
question.
sure.
So, what do you think the different way of expanding grid will affect the phenomenon? What do you think? How?
Like, how do you mean?
How the different ways of expanding grid affect the phenomenon?
Like when the balloon is inflated, it will be bigger, right? So it will affect the
Okay. So you have discussed with the reporter about the net pressure,
yes.
but some of the part the net didn't touch the balloon as well.
Like as I mentioned in I use delta P times A, right? And A means the surface area with the balloon.
Can I say? Because in my experimental setup, the balloon is like this. In the match, it's like this also. So, sorry.
So next question. You use the let me see, how do you pump the air?
Two ways. One is like this one.
Okay, so another one to do, can you ensure the balloon here is the same as the balloon you pump in the balloon, because the pressure will vary.
This is the syringe of volume that I pumped in, and the V of the balloon will be I'll measure it using drainage method.
Okay, time is up. Preparation for the reviewer. In 2 minutes. For the review, please take the floor using 4 minutes.
Okay, I'm the reviewer from Team Ridiculous, and today I'm going to review the problem number 2, aerosol. So these are some generally pros and cons. Comments for reporter is the pros consists of like clear definition of terms, affable theory, detailed explanation of experimental setup, and they analyze the data comprehensively, clear comparison factors in experiments, and have measured the pressure and several variables. However, there are some areas for improvement is unclear notation for experimental data, unquantified conclusion, and using same kind of balloon. No, they didn't tell us they used the same kind of balloon, and experimental results did not correspond to the theory, and there are lack of experimental videos. Okay, and now is some comments for opponent. The pros is point out the important variables in this experiment, like elastic, fatigue, Young's modulus, and they are sagacious and perspicacious, and they have a very clear focuses. Nonetheless, there are still some areas for improvement. They did not deepen the discussion by further questioning. They have no follow-up questions, and they announced during the discussions which really interrupt us, and they consider the pressure in balloon will be small, which is definitely wrong, and using the ball model, but actually the balloon is it is not a ball. Oh, and then I will conclude their discussion. In the discussion, they explain how the Young's modulus can be applied, and also the opponents seek to ensure that if the balloon is the same from the beginning to the end of the experiments, and they draw the graph of the force and the balloon to make us more easy to understand the phenomenon, and also the opponent suggests using the another theory to describe the gas instead of the ideal gas equation, and also I have asked a few questions like I follow up the Young's modulus questions. However, I think in their discussion I didn't see so much discussion about the data analysis. So I think this is something they can enhance. And for my quick questions, I asked about the elasticity of the balloon, and because the reporter from the presentation and also the discussion didn't mention the elasticity of the balloon, and also the measurement of the Young's modulus is unclear. And like the opponent and the reporter, they have discussed about the net pressure, and also I have asked about the grid extent, and the opponent also agreed with me that this is a very critical factor. So but they didn't discover that if they change the length of the net, then the balloon will have a displacement which will affect the phenomenon. And so this is my summary. Thank you.
Okay, questions from the juror. Okay, sorry. Conclusion for the report.
I'm the reporter of this question, and from our discussion, we have said that the reporter just mentioned that I didn't talk about the fatigue of the balloon, but actually in my discussion with the opponent, we did say about that we will check the balloon is elastic and is the same before we do the experiment. And the opponent suggests to use another theory to explain the experiment. However, we don't think that's necessary due to the opponent just said that using the other equation is because they think that the pressure inside of it is small, and the but however we think that the pressure, how to quantify the big and the low is not. The opponent didn't mention it very clear, and we think that the PV equals to the ideal gas law is suitable for our experiment. And also they think that the opponent just said that we have to use Arduino or something to track the temperature of the balloon, and the outside of the air is the same to maintain it. And I actually want the opponent to say more about, in our discussion, about how he will do if he's in his experiment.
Okay, thank you. Question is going to
This is a composite muscle, right? Because it consists of balloon and the net. So your results should reflect the properties of these two components. One is the net, the other is the balloon, right? The balloon is characterized by its elasticity. The balloon is not a short film. We're talking about surface tension is not correct. But there's a membrane. The membrane has the elasticity. Shouldn't that be included in your analysis?
Yes, absolutely. I believe that I should put that I did check the elasticity of the balloon before I experienced. And also
But you
mention,
didn't give any reference to your measurement. There's no measurement.
I did.
You only give us how much air is pumped in. So,
The air.
okay, yeah. This is the opponent, is that right? This is the opponent, right? And I think your comment on your suggestion of using van der Waals equations for gas. What's your reason?
Because we think that the pressure inside the balloon is not big enough to use.
How big is big?
Like 5 times of the air pressure.
Excuse me, 5 times atmospheric pressure. That's not good. Vacuum is low. Vacuum pressure is low. I'm surprised that if you study the property of the muscle, you should apply force from both ends, right? And then see how much it stretches actually and laterally. In points of the lateral parameters should be affected by the balloon.
So I did fix the size.
You did what?
Fix the size of the balloon. And also fix the size of the mesh. So they're the same.
How did you fix the size of the balloon?
By
You-
using this.
You inflate it with different pressures, right? So it has different pressures, right?
And in some of the experiment, it's the same it's the same pressure that I included. For example,
My question is, it shouldn't be the same. It should study its effect on the lateral strength.
yes, but I'll calculate it, so I'll know that it's different. And so if I know this, then I'll divide it by the strength, so that I'll get the Young's modulus. And because that's different, so I'll calculate.
The sigma is the strength, strength of the net, right?
The sigma is the stress.
What's per unit area? Strength. Strength, that's called
Stress, yes.
sigma is strength. Yeah, of course, it's like pressure.
Okay, let's go this time.
Sorry, we're taking up all the time.
Okay, ready? Opponent, reporter. 77665 for the opponent. 77765 for the reviewer. 87775. Okay, let's take a 10-minute break.